Continuing with the multi-layer perceptron concept, and in the previous lecture we started with the basic concept of multi-layer perceptron, that it is an extension of the logistic regression, and that it can be, the perceptrons can be used to solve simpler problems such as AND operation, OR operation. We can use it to solve such kind of problems where we have the linear boundary. And the idea is that we can place a hyperplane in the pattern space, and then we move that plane until the error is reduced. So we draw a linear boundary so as to minimize the error. So for example, in your AND operation, we can define our plane like this. This is our pattern space. So in this example, we are able to separate the linear space for the AND operation. So we can use the perceptron for these simple problems. However, the problems, they are not linearly separable mostly, and for that we can use the multi-layer perceptron. So we first studied the logistic regression and what is binary classification and how can we define a linear classifier. Then we extended that concept into multi-classes, and if the boundary is not simply linear, then we can also use multi-layer perceptron to solve the problem. We defined another format of our classifier, h of x, and the hyperplane is determined by this function. We represented the perceptron graphically in this format, where each weight is multiplied by the input values, and then they are summed up. This gives us the function s, the result s, which is input into our classifier function to obtain our y values. So we call that an artificial neuron, because it mimics the function of the human brain neurons. And what about if we combine many perceptrons to solve nonlinear boundary problems? So we had the hard limit, where sum of these values, if it is greater than 0, the answer is 1, otherwise 0. The same statement here. This is the basic linear equation that is used to solve this problem. For the AND, we have to set the weight values. Here we have set the weight values to 1 and 1. And W0 to be minus 1.5, such that the sum is calculated, and if that sum it is less than 0, or otherwise it is assigned a 0, and if it is greater than 0 we assign it a 1. So if it is greater than 0, which is 0.5 only in this example, we say it is 1, otherwise it is 0. So this is how we define an AND operation. We know that if the values are dissimilar or 0, AND operation gives us a 0 value, otherwise 1. So this is how we designed an AND operation using the perceptron, single perceptron, and of course we can also design the OR operation, where we set the weight values to 1, 1 and then 0.5, such that all the values gives us 1 and only 1 will give us 0. So this is how we design the OR operation, and this is our linear boundary that we have determined for this equation. I will rewrite, sorry. So we do the sum and then put the value into the classifier function f, and if we put these values, check for these values or class, and here important factor I mentioned was the setting of the weight values is important to convert our problem either into or AND operation. And for NOT operation we only need one variable and set the weight values accordingly so that our function can work as, this neuron can work as a NOT operation. And cascading multiple neurons converts it into a multi-layer perceptron, where the input first goes into your first hidden layer, and then you can have multiple hidden layers also, and then you have your finally output, and you put the classifier function at the output layer, and the number of input neurons and the output neurons depends on your problem, what you have designed and are trying to solve. For a binary problem you will have only one node at the output, but for digit classification, for example, you will have 10 nodes at the output. And we discussed that each neuron has a summation part and a non-convex function f, nonlinear function f, and we have a summation part and the function part, and here your h1 will be calculated by the summation part. So h1 has the input from w11, w12, w10, w11, w12, w10, and multiplied by x1, x2, and 1. And then this is your function f to create your h1 function. And that h1 and your h2 are then input into the next layer. Here in the next layer we have the output layer, so they will be input into your next layer, the output layer. We have an additional w30 here, weight value, to estimate our y. So first sum the h1 part, the h2 part, which is itself a combination of w and x, w's and x's, and then you take the function apply the f function to get your output. So multilayer perceptron consists of the input layer, the hidden layer, and the output layer. So simply pass the input values to the next layer, and the nodes in your first layer will depend on the number of inputs that you have. And on the hidden layer, there can be several hidden layers, and the number of nodes should be given in advance, decided in advance. And then you have your output layer, and the number of neurons at the output layer depend on your designed problem. Okay, so for a Boolean function, you can have a 2-layer perceptron. For continuous function, you can use 2 layers, and for any arbitrary function, you can design multiple layers or multiple neurons depending on your problem. For example, in this case, we have a problem which cannot be simply solved by defining a linear boundary, and it cannot be simply solved by a single perceptron. So we have to first define these lines. Okay, so first define the lines in the first layer. Then we have to define how we are going to combine or define the convex lines. Because the region is not separated by a simple multilayer perceptron, we can see that the MLP can be used to learn the arbitrary areas, while a 2-layer MLP can learn the convex region. So what is the convex region? If you can draw a line from any point in the region to any other region, and the line passes out of the region, then the area is not convex. So the area that is defined by these 2 lines, and if you can go out of this region, that area is not convex. That is how we define the convex area. So we can use multiple perceptrons, neurons, to define first the lines, and then see how they're the convex regions we can define, and then we can combine the convex regions. So first, for example, we define this region, then the next region is defined like this, right? So separately we define this region, and separately we define this region, and then in the last layer we combine all of them. So now we have separated our plus and minus values using the multi-layer perceptron. I will go into the detail further as an example. To solve a non-linearly separable problem such as the XOR operation. So in the XOR operation, we know, for example, we have or given x1 and x2, 0, 1 and 0, 2. We know that the pattern space can be defined in this way. This is your pattern space. At point 0, 0, then you have 1. So here it is 0, here it is 0, this point it is 1, and at this point it is 1. Let us draw it. That is represented over here. So at this point is 0, it is 0 over here, it is 1 here and 1 here. This is your x1 and this is your x2. So when x1 and x2 are 0, 0, zero, 0, the value is 0, like over here. And if your value is 1 and 0, okay, so your x2 is 1 and x1 is 0. So this point again is a 0. So this problem cannot be solved, as we can see, using